Okay, good morning everyone. My name is Miguel Duarte. I'm here with Federico Paulinelli, which is essentially the blood, the sweat, and the tears behind the project that will enable the things we are about to show. And we're here to present a talk titled Weaving the Fabric, which is about EVPN overlays for multi-cluster KubeVirt deployments. The agenda will be, we will begin with a motivation, then go through what EVPN is, which essentially is like a short disclaimer, the enabling technology for this. Federico will explain to us everything about the implementation of this. Then we'll show a few demos and finalize with the conclusions, in which we'll pretty much be telling you a summary of everything we just told you. Now, first thing, why should you care about any of this? So, the use cases for multi-cluster could be kind of intuitive, but let's go through them nevertheless. So let's say that you have a single cluster in, like, I don't know, a bare metal cluster located in a building, and for whatever reason, everything goes down. You lose power in it. After a while, everything goes down. Like the blast radius is huge. Something happens, your entire set of applications go down. If you have multiple clusters and your application is spread across them, well, it will keep working. So that's one thing. We want to have resiliency for your applications. Things like scaling, hybrid cloud also require you to have your multiple clusters interconnected. And the third thing, which is very useful, is legacy applications. So I'm guessing if you are running VMs, you have probably seen a virtual machine whose identity is pretty much an IP address. So that means that throughout the life of a VM, in probably 20 years, you cannot change its IP. It needs to connect to the same network. It needs to reach the same neighbor throughout history. So you need it to be connected to the same subnet. And you probably have changed the platform many times. So these are the reasons of why should you want to have like multiple interconnected clusters, and we will be doing that using a stretched layer 2 network. So, as I said, goal is twofold. First one, we want to have a stretched layer 2 network, and this will be very useful to provide us these two features: cross-cluster live migration and resource pooling. So in a way, you have multiple clusters, but you'll be providing a unified front of resources to the users. The second use case is routing between these different networks using a VPN. Here you'll be able to provide traffic segregation and also direct routed ingress to the virtual machines. What does this mean? It means that, remember, this is KubeVirt, so your VMs actually run in pods, and this means that you no longer need to expose services or use NAT. So, EVPN will be our enabling technology of sorts. It will provide us the ability of having a stretched layer 2 network. It will also provide us with the other objective we have, which is to route between these different networks. And it has some characteristics. First of which, and most important, at least to me, is that it has reduced broadcast, unknown, unicast, and multicast traffic. So let's say you have, I don't know, 100 clusters that are interconnected. Each of them is running thousands of pods and hundreds of VMs. Imagine the amount of neighbor discovery messages that are happening throughout this scattered clusters or ARPs. That is just too much. We don't want to have that. It needs to be more efficient. And EVPN provides all of that. And remember, we're here to see like seamless workload mobility. That's what we want to have. We want to see a VM migrate from one cluster to another without impacting the applications running in it. So, EVPN first stands for Ethernet VPN, and we can see it as a twofold protocol. So, in the control plane, it runs multi-protocol BGP, and the data plane can be multiple implementations like VXLAN, MPLS, SRv6. In this presentation, the component we're using pretty much just has a single implementation, which is VXLAN, which is why it is in bold. And let me begin with the control plane. So as I said before, this is using multi-protocol BGP, and essentially it provides two things on top of BGP, which is a type 2 route, we'll see what this is in a minute, and a type 5 route. We'll see what this is in probably 2 minutes. So, type 2 route. Whenever a VM connects to the network, this will we'll create a type 2 route, which is essentially a means for you to register to the entire network scattered throughout these clusters that the way for you to reach this MAC and IP address is via this next hop. So you're essentially broadcasting to the network that for you to reach this VM, you need to use this particular next hop. A type 5 route, on the other hand, is the same concept, but not for a MAC and IP. You're just saying the entire prefix. So this entire subnet can be reachable via this next hop. You're essentially advertising how to reach either a MAC and IP pair, a MAC address, or an entire prefix. And I'm going to hand this over to Federico, and he will explain this in more detail.
Okay, so now let's have a look at how we try to implement all this thing, while we keep it sane, and we try to follow some design principles. One was try to integrate existing solutions, not to reinvent the wheel, to have something that is composable and pluggable with existing building blocks, or to reuse as much building blocks as we had. The other thing is we wanted to have something that is kind of primary CNI agnostic and also can work on some secondary Multus plugins. And this is what driven our whole architecture. So the building blocks are obviously KubeVirt. We need that to run our virtual machines on Kubernetes clusters. These can work with any bridge-based CNI. The two most famous are OVS CNI and Bridge CNI. They are used to connect your secondary networks either to an OVS bridge or to a Linux bridge. And there is this other thing in the middle, which is OpenPERouter. It's a new project that we've been working on more or less for the past year. And it's about running a router on your Kubernetes cluster. So the idea is of the project, and if you are interested into this, we have a full-fledged talk in the networking dev room later today. The idea is to have a router as a Kubernetes component that you can deploy in your cluster with Helm charts or manifests, and basically it will handle all the complexity of being a router, exposing the interfaces to the host as a real router as VEF pairs. It allows you to integrate with BGP speaking components such as Calico and MetalDB, but also, and the focus of this talk is, you have this kind of dangling wire on the host that allows you to enter a broader layer 2 overlay spread across multiple nodes. And this is how more or less the architecture is done. So OpenPERouter allows you to expose this leg on the host. You can attach it to a Linux bridge on the host or to an OVS bridge, and you also have facilities to have this bridge auto-created for you, and all the rest is handled by Multus. So you just use a secondary network, bridge CNI, you connect your VM's secondary network to that bridge, and the magic happens, hopefully. This supports distributed Anycast gateway, so your local gateway is going to be the same whenever the virtual machine runs, and this enables some interesting features as we are going to demo later on. So, in words, it's simple. The reality is that in order to enable EVPN on a Linux host, you have to do a lot of things. You need to configure Linux bridges, you need to configure Linux VRFs, VXLAN interfaces, VEF pairs, and doing it manually or with some automation is a lot. That's why we try to put together something that handles this complexity for us behind a cloud-native approach. So you can scale, you have 1,000 nodes, you craft your nice or not so nice YAML, you throw it at the cluster, and boom, you have EVPN. Yeah. So this is what OpenPErouter is just a Kubernetes controller. We don't focus on a particular CNI plugin, so it can work with your primary CNI of choice, and it allows us to scale our deployment in an efficient manner. So what do we need in order to have EVPN configured on the cluster? You need virtual tunnel endpoints, which is the end of the tunnel or the start of the tunnel, and you need the tunnel. That's the basic thing that you have to do as a starter. In order to do that, we have this CRD. It's called underlay. Basically, it's the details of the session between your top-of-the-rack switch that now becomes number, because all the VPN logic is done inside the node. And then you need some extra things like the interface that you want to use to connect to the top of the rack, and a CIDR, because we want, I can show it on the next slide, we want the VTEP on each node to be different. And so like we leverage the Kubernetes way to do things, and we synchronize, and each node gets a different IP. And of course, the data plane is VXLAN. So what really happens is that the traffic coming from the host gets encapsulated in a UDP message with the local VTEP as a source IP and the destination VTEP as the destination IP. How do I know where do I need to send the packet? This is the type 2 routes that Miguel was telling us about. So the BGP fabric knows how to announce the locality of each MAC and each IP around the fabric.
Sorry for this. Whoops. Okay, so now how do you create the control plane for this? Again, you throw a YAML at the cluster, and this OpenPErouter thingy will just bend over backwards, create the VRFs, the bridges, everything put together for it to just work, which essentially will get you a stretched layer 2 network, an overlay across the entire fabric. By fabric, I actually mean a bunch of connected routers, which could be like the internet itself. And this is what an L2 VNI looks like. There are three very important things here. First, VNI. So this is a VXLAN concept akin to the VLAN ID for it. The VRF, which is pretty much like the identity of this. And we'll see later on how to integrate this, expose this network to the outside world. And finally, the host master, which is how do you provide connectivity from the router to the host itself, or to the Kubernetes node it runs on. Essentially, this is what it looks like. So you have your Kubernetes node. It has the router running on it. Like the blue thing is the network namespace of the router. And for every VNI that you have created, you'll have a bridge like that one. And then you'll be having a dangling VEF on the host. And depending on the configuration, like if you remember, you've seen here that we are using a host master of type Linux bridge, auto create. It will create a bridge on the host for you. What do you do with this bridge now? This bridge is essentially what your workloads will be using to attach to the network. So you will, if you're used to Maltas, you will just provision now a network attachment definition with a configuration pointed to the bridge with the proper name, and you'll be attaching to that bridge, which essentially is this. So we have our KubeVirt VM running there, attached to that bridge, which is using that VEF pair, attaching to OpenPErouter, and then it will use the VXLAN tunnel Federico told us everything about later, a little bit ago. Now, I'm having this part here to explain how the type 2 routes work. So whenever a workload attaches to this bridge, it will add an entry of this MAC address is available on this Linux bridge port, right? This will be reflected on the FDB table, right? And FRR Zebra will provision a type 2 route. and this is it. Whenever the other nodes, which could be in different clusters, see this type 2 route, what will happen is they will provision an entry in their FTP table. So they will know this MAC address is available on this VTAP IP, which is somewhere else in the world. This is for a type 2 route that has just a MAC address, as you see in the bottom, right here. Now, in order for you to jump into another network, you will also need to have an IP address, right? So there are type 2 routes that have MAC and IP addresses. Pretty much the same concept. Whenever the workload attaches to the bridge, it will send or a neighbor discovery protocol or an ARP request reply. This will appear in the neighbor table. FRR Zebra will see this thing, will provision a type 2 route with MAC and IP address that we see there in the bottom, and this will be advertised in the fabric. Whenever a different node sees a type 2 route with a MAC and IP address, it will pretty much just provision a static entry in their neighbor table, and everybody will know this VM is available via this VTAP IP, which could be somewhere else in the world. Beyond layer 2, well, we have the ability of connecting different routes using these type 5 routes. I do not have a sequence diagram for that, but it's the same concept, but instead of being FDB tables or ARP or neighbor tables, it will be the route table. And this will allow you to access services in these other networks and to provide direct routed ingress into the VMs. This means that you will be able to access to it using directly the IP address of the VM. So no need for NAT, no services, nothing like that. By services, I mean no Kubernetes services again. And this is how it looks like. The key thing here is the VNI must be different than the one you've specified for your L2 VNI, but the VRF must be the same. That is how you connect a layer 3 VNI to a layer 2 VNI. So essentially, how you expose your stretched layer 2 network to the outside world. Essentially, this just turns out to having an IP address on your gateway, on the bridge's management interface, and a VRF encapsulating all those routes. Oh boy. Could you get me like the in there? There's a thing. So, okay, let's skip this. Let's go to the demo right now. So what we will see right now. So we will have two different kind clusters. These kind clusters will have workloads running in them. Wait a second. It's done? Thank you. Huge thanks. You saved us. I owe you a beer. So again, VMs running in different kind clusters. Everything is in this laptop, but this is just to showcase a concept. This could have been like throughout the internet. And then we will have a host on a separate network that will try to access them. We will see two things. First, we will see a stretched layer 2 network. So these two guys will be in the same layer 2 overlay. And we will see another interesting thing. We will see live migration. We will have this host A pinging this VM right here, and then we will trigger a migration to this other cluster while this ping is working. And we will see how the traffic behaves. Hopefully, not many packets will be dropped. So you can scan this for a link to the ASCII-NEMA demo. There's a link to the script that runs this demo for you, so you can do this at your home. Okay, now this is the recording. Unfortunately, this won't be a live demo. I hope the font is big enough. But let's see. So, okay, whoops. So in the upper left, I have the VM running in cluster A. In the I can. Okay. In the upper right, I have the cluster B. So it has a different VM running in it, and this is where the VM1 is going to be migrated to. That is why, if you look there, there's also a VM1, but it's waiting for sync. Jenia right there will, in a couple of minutes, explain to us everything about cross-cluster live migration, but for now, keep this in mind. VM1 running cluster A, VM2 running cluster B will communicate from one another, and at the bottom, we have the script. So, okay, details. IP address and MAC address of our VM1, IP address of our VM2, which is running on a different cluster, and the receiver thing, which is the copy of the first VM. Okay, this is running. Now we're going to ping from the client, so the thing that is outside a cluster, it reached VM1, it reached VM2, so we have connectivity from a different network to these two VMs running in different clusters. And I'm just going to show that this essentially is in a different network. If you see, VMs are in the 170 IP range, and this one is in the 192, 168. So I'm going to console into the VM, and I'm going to ping. This was too fast. So from VM1, I'm going to ping the other VM, which is the .31. So we have a stretched layer 2 between two different Kubernetes clusters. That was the first demo. Second demo will be seen now. So this, I'm going to show you the type 2 route. So we see here a type 2 route for just a MAC address, but it is telling you to reach this MAC, this is the next hop you're going to be using. Interesting here also, MM2. This is MAC mobility. We'll be seeing this in a while. And then same information for the other virtual machine. It managed to ping. This pretty much essentially means that we have started to ping from our client into our VM1. I'm just putting here another ping so you see that I'm not lying. I've provisioned the migration in the destination cluster. That is why the VM1 did something weird there. And I will now trigger the migration in the source. That is why the virtual machine went to scheduling on the destination cluster. So I want you to look at this, seeing ping is working, and I want you to look at this here, saying virtual machine 1 is available via this next hop, meaning cluster A. And traffic is working, and the migration, the VM is pretty much being copied. It'll take a little bit of time. Still cluster A, scheduled, it knows to which node it'll be, and it moved to cluster B right here. So this virtual machine, meaning this type 2 route, like this MAC and IP address, is now available in cluster B, which has a different next hop IP address. And as you've seen, the ping is going at it like nothing happened. It's not exactly like nothing happened. We'll see here, like we've lost 4 packets during the migration. We are using 100 millisecond intervals. So this totally amounts to like probably 400 milliseconds of drop traffic. It's not insanely good, but it is quite good. And I think this concludes the demo, and I can leave this now to Federico to walk us through the conclusions.
Okay, wrapping up, we saw how we can leverage existing building blocks to implement a broader layer 2 overlay across different clusters. We showed how you can wrap that layer 2 domain into a layer 3 domain and having routable IPs from outside. And I want to stress this. It is in the very same way you would interact with a real router with VLANs. So you have your VMs today with the Mac VLAN CNI plugin as a secondary interface. You have your VLAN coming from the router. You have your tunneling mechanism implemented into the router. Nothing changes from the VM. It's the same, but with a component that is running on the Kubernetes cluster, which is, I think, the nicest bit of this implementation. The fact that we are not reinventing the wheel, but reusing existing mechanisms to have a Kubernetes native way to do this. And of course, live migration is the cherry on the cake. Yeah, this is more or less the end. Some resources, we try to keep the documentation aligned and nice to use. There are a couple of blog posts on the KubeVirt official blog. In the OpenPERouter documentation and repository, we are trying to keep a lot of examples on how you would integrate the project with existing components, with the scripts and automation that you can run on your laptop. And time is up. FRR is the engine for the routes, and that's it. If you have any questions, we are going to be around.